some questions. You guys have questions from homework stuff? Blake?
I do have a question. If you wouldn't mind doing number 19 on 3.8.
19 from 3.8.
Yes.
Okay. All right. It says if 3% or $3,000 is invested at 5% interest, find the value of the investment at the end of 5 years if the interest is compounded annually, semi-annually, monthly, weekly, daily, continuously. Okay. So probably the easiest would have been if you remembered the formulas for these.
Yeah, that was like the very last section.
Yeah, we did this last year. So all of them I'd use that first formula except for the last one where it's continuous. I'm going to use that special formula. Note that this is, like our the same form as our derivative or solution to our differential equation that we've been seeing throughout, right? And really this one is even also, like, if I think about this is oops. That should be, come on, to the t. But like that's still the same thing, right? Where all this junk in here is our k now. So still the same thing. I think it'd be easier just to jump to the formulas that you knew to do this rather than like stumbling through like figuring out what the k is or whatever. Are you good with just plugging stuff in from there, Blake?
Yeah.
Yeah. So the thing you remember here is that like these words give us our value for n, right? For daily, I guess I'm assuming it's a non-leap year. And when n is infinite, that's where we run into the getting the e there. Okay. So that's part A. That's all I'm basically doing is just plugging the junk into those formulas. Part B, it says A of t is the amount of the investment at time t for the case of continuously compounding. Great. Write a differential equation and an initial condition satisfied by A of t. So our differential equation that we've been writing for this whole chapter has basically been kind of this form. So my differential equation is like, they used in the notes, it was like dy dt times equals ky. But in this problem, it's telling us that A is the thing we're talking about. So it's dA dt equals Ka. And then our initial condition would be just the value of the function at time 0. So that's easy. That's just $3,000, right? That's the initial condition for our value of our function. And if I go back here, the k is going to be the same thing as that exponent, which was just 0.05. There's my differential equation. There's my initial condition. I'm done.
Oh.
There's nothing more to do. It's just like a, do we understand the notation question? Whereas confusing because the verbiage and like difficult to understand, but what is it really asking us to do? Like, not really very much.
Yeah.
It's basically going backwards, right? Before we had always had, we started with like the differential, or started by building out the equation. Here we're going backwards from the solution to our differential equation, that general equation, and rewriting the differential. But it's like, okay, whatever. Is that okay?
Yeah.
Okay. Yeah, I mean, it's, and again, like not much to do, which is great. I love those ones.
Yeah.
It's like, oh, that's not a half a page of writing? Fabulous.
Yeah.
Fabulous. Others, who else has some stuff? John?
5.
Same section, number 5? Sure. Let's move that over a little bit. Says the table gives estimates of the world populations in millions from 1750 to 2000. Part A, use the exponential model and population figures for 1750 and 1800 to predict the world population in 1900 and 1950. Compare with the actual figures. Okay, so the exponential model is here. So there's two things we need to find. We need to find P naught and we need to find K. So if I'm going to use 1750 and 1800, so I'll call, I don't know, do that, I guess. Actually, let's just do this. I'm going to call this times 0. This will just simplify everything. It'll give me, it'll just be equivalent. So if I do that, then P0 is just 1790. Okay? And then that makes 1800 T50. So that's going to be 790 e to the k 50 equals 980. So divide both sides by 790. Take the natural log of both sides and then divide by 50. To get the k by itself. And I'd probably hang on to all the decimals there. So my model then is going to be that at, and then it wants me to approximate the populations at 900 or 1900 and 1950. So this is t equals 150 and t equals 200. And now I'm just going to go break out my calculator.
Yeah, I was confused about the model. I see.
But I think that's all I need to do. Let's just grind through this and double check here. Do you have the answer sitting in front of you from the back of the book? Okay. We'll check that in just a second then. So 1508 million, I assume. These are populations in millions. Yep. And then if we do, just change that to 200. So 1870 million. Let's look real quick. This is 3/8 that we're looking at, right? Number 5. 1508 and 1871. Yeah, good. And if I compare those numbers to what we get in the table, we undershot, right? Part B says try it again, but we're using the figures from 1850 and 1900 to predict 1950, so it's the same process again. Are you cool?
Yeah.
And then part C, it says use 1900, 1950 to predict for 2000. Again, the same process. So there you go. That's okay.
Yeah.
And it says try to explain the discrepancy. It's the problem's going to be like it is like a real world, like what's going on in the world between 1900 and 1950. You had like a global pandemic, 2 world wars, a bunch of stuff driving down population, and then relative peace and prosperity from 1950 forward.
Yeah.
So, Blake?
So for like B and C though, can you also just set like 1850 to 0 and then 1950?
Yeah.
Perfect.
Yeah.
Okay.
Yeah. Absolutely. Do it that way.
Just want to make sure that was like allowed.
Yeah. It's making a new model. Mm-hmm. So at that point you can set whatever you want. Is since all the years are just years, and all that's essentially doing is just like shifting everything left or right, but everything else stays in the exact same relationship to itself.
Yeah.
So it's fine to do that because as long as you're doing that shift for everything, if you needed 1700, then you'd have to use a negative time, which is like a weird thing to do, but it'll give you the right number. But like, yes, do that. Makes life exceptionally or massively easier than being stuck solving some crummy system with logarithms in it or something. Cool. Luke?
3.9, number 5.
That was the one that we had asked you guys to do?
Yeah.
Okay. Any other questions before we transition into the related rate stuff? Which is fine. We're going to go through those two together, but I wanted to be like the last things we do because then we'll do some more related rate examples and move into that. I just want to give anybody else a chance if they had any other homework stuffs before we start in on the related rate stuff again. Okay, fair enough. Let's go do that then. So we'll do 3 first, and then we'll also do 5. Because 5 is a little trickier. Good to start with 3, especially because these are things I asked you guys to all look at and because we wanted to go through together. All right, so it says, excuse me, each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? Okay. So, what are we, this quantity here, 6 centimeters per second. Well, that's actually, what equation were we going to be using to describe this? Yeah, area is equal to s squared, right? Where s is the side length of our square. Okay. So 6 centimeters per second said each side of the square is increasing at a rate of 6 centimeters per second. So what is 6 centimeters? What name should we give 6 centimeters per second? That variable. ds dt. Very good. It says at what rate is the area of the square increasing? So what name are we going to give that? Great. And it's saying we want to find that when the area is 16 centimeters squared. Okay. All right, so let's go ahead and take the derivative of our equation then. What's the derivative of A? dA dt. The derivative of s squared is 2s ds dt. Okay. So we're looking for dA dt. We have a value for ds dt. What don't we have a value for? S. But what haven't we used yet? Haven't used the fact that the area is, when this dA dt that we're looking for is 16 square centimeters. So what can I do with that? Yeah, I can use that to find s. And the unit should be centimeters squared per second. Great. I know it's centimeters because the units everywhere else were centimeters. I know it's squared because it's an area. And I know it's per second because the other rate was given in per second. And that's all she wrote. Is that okay with you guys? Okay. Let's look at. No, it's okay.
The 4 and 6, or like there's like a disconnect, like the stuff that where you put the dA or dt equals 2s.
Mm-hmm.
That, and then what did you do right after that?
So s is 4. So I plugged in a 4.
How do we? Oh, because 4 by 4.
Mm-hmm.
Okay, I've seen that.
And ds dt is 6. So I plugged in the 6.
Oh, I see.
Is that okay?
Yes, it's good.
Fair, yeah, no problem. Again, if there's like you feel like you're missing something, you stop me and ask. No big deal. This is your first time doing it. It's my like 100th time doing it. So if it's like feels like something easy happened here, but I'm just not seeing it, like stop me and ask. Totally fine. All right. A cylindrical tank with radius 5 meters is being filled with water at a rate of 3 meters or 3 cubic meters per minute. How fast is the height of the water increasing? I'll draw myself a picture. So here's my cylinder. It's like my water spigot. Actually. So there's some water coming in. Look at this artwork, guys. All right. We're told that the radius of this tank is 5. So I'm going to call that R sub t, because we also have a second radius. What's the other radius in this problem? Radius for the water, right? What's the radius for the water? 5. In fact, what is the radius going to be anywhere in this cylinder? 5, which means that R is a constant. That's important. We'll see where in a moment. Okay, and we're told that the water is being, or the tank is being filled with water at a rate of 3 meters or 3 cubic meters per minute. What is that quantity going to be called?
dV over dt.
And I'm going to put a subscript of W on that for the volume to indicate that that's the volume of the water per time is changing, not the volume of the tank, right? Because there's 2 separate volumes going on here. So the shape of the water is going to be what shape? It's a cylinder. Okay, what's the volume of a cylinder equation? Yeah, it's the area of the base, pi r squared, times the height. And I'm going to put little subscripts of W on these to remind us that we're talking about the water and not the tank. Everybody's cool with that? Now, remember that R is a constant. So if I differentiate now, there's no product rule. I get no dr dt quantity. Everybody agree? So let's go ahead and do that. Because what are we looking for in this problem? Yeah. Which we have, right? So all I need to do is divide both sides by, well, really, that's like, yeah. So 1 over 25 pi times 3 is going to equal, and when I type that into my calculator, I get about, I don't have this one written down on my notes. Of course not, it's a homework problem. Yuck. Just do it this way. 0.038. And what unit should I have on this? Meters per minute. And if you want to change the decimal point, I guess you could if you wanted to. Jack?
This might be kind of a tough question, but
It's okay. These are the important questions to ask.
if I wrote it as like 3 over 25 pi, that's not wrong.
Correct. Not wrong.
That's just how I wrote it.
Yeah.
And I just want to make sure.
Yeah. No.
That's okay.
On a problem like this, almost assuredly the final answer on a multiple choice even be represented as a decimal. Although I guess I wouldn't be shocked if they had an exact answer like that, but I'd be a little surprised. And certainly on a free response situation, either would be acceptable unless the directions specifically ask for like an answer in terms of pi or something. Although I'd find that surprising again.
Okay. Thank you.
Unless it was like not a calculator active problem or something. Everybody cool? I'm going to go back to the 3.9 page here. We'll just kind of continue with some more examples, okay? So you notice on that previous problem, I was being really careful about labeling things as the tank versus the water. Now, did it really matter in this problem that I was that picky about it? You didn't really run into any issue there. Where that is gonna become an issue is if the shape of the container you're filling isn't constant throughout, right? Like the cylinder here for the water has the same radius everywhere in it. Let's look at this next example in 3.9. Here it says a water tank has the shape of an inverted circular cone. It says that the base has a radius of 2. And has a height of 4. If water is being pumped into the tank at a rate of 2 cubic meters per minute, seems like a popular rate, find the rate at which the water level is rising when the water is 3 meters deep. So here, RW, we don't know. And note that RW is not the same as RT. Everybody agree? At each height, that water's radius is going to be different. Okay. So that's our picture. Wish I could color maybe a little bit. All right. What equation are we going to be using to describe this situation? Volume of a cone. Great. The volume for a cone is 1/3 pi r squared h. Yep. And are we talking up what part of what cone is changing? The tank or the water? The water. So I'm going to do again. I'm going to be specific here and put the subscripts with the water. Oh, come on back. There you go. Everybody's cool? Okay. Now, notice here that the radius and the height are both variable. If I differentiate this step, what do I need to do? Product rule. And if I differentiate this step, I'm going to get an RW and a dRdW. Do I have information about? Oh, I guess we didn't write down what else we have yet. Let's write down what we have, right? So we have RT and HT. I wrote those down. What is, says the water being pumped into the tank at a rate of 2 cubic meters per minute. What is that? Yeah. Why did I put a 3 there? That's like a sideways W or something, Mr. Kulik. You're a crazy man. It has been that kind of a morning. And then it says, find the rate at which the water level is rising. So that's DH for the water. When the water is 3 meters deep. Everybody's cool with that? So again, back to our conversation. If I differentiate with what I have right now, I'd have to use a product rule. I'd end up still with RW in my equation, which I do not know, and a DRW dt which I also do not know. That'll be a big problem. What I want to do is I want to find a way to get rid of the RW in this equation. Take a look at the picture we've drawn. There's a set of similar triangles in this equation. So I have one similar triangle here. And a second similar triangle there. Why do I know those two triangles are similar? All the angles are congruent, right? The two radii are parallel, so all those angles are corresponding, so they're all congruent. Does that feel okay? All right. So let's just redraw that real quick so that we can see. So this is RT, and this is HT, and that's similar to our little triangle, which is RW and HW. Everybody cool with that?
What is the symbol as the hypotenuse of the first triangle?
I don't have one, but I don't need one. That's a similar sign.
Oh.
That's the squiggly that's showing, like, I'm just saying those two triangles are similar. That's the symbol we use from geometry to show for similarity. That's not the, yeah, we'll make that black or something, right? It'll be less confusing if you go back and look at it. That's a terrible looking similarity symbol now. Let's try it one more time. Yeah, it still sucks. Whatever, I'm over it. All right. So I have these two triangles that are similar. What can I do with, or what can I say about similar triangles? The ratio of side lengths is proportional. That's right. So I can say that RT over HT is equal to RW over HW. Or you could say that, like, HW over HT is equal to RW over RT, or, you know, arrange it in a bunch of different ways that are all equivalent. Everybody's cool there? I can multiply both sides then by HW to solve for RW, which is great because HW is already in my equation, so it's not going to be adding a new variable. And RT is a constant, and HT is a constant. So I can then replace RW in my volume equation with HW over 2.
Oh, we can't say that HW is 3 because of the changes.
Not yet. We have to take the derivative first, and then we can plug in.
All right.
Because right now, for this equation, this is true for all H.
Yeah.
And when we differentiate, it still needs to be true for all H. But we're interested at a specific H. But we need to do the derivative before we plug in. Okay. So we have now volume equals 1/3 pi. And then we have, instead of R squared, we're going to have HW over 2 squared times HW. Let's simplify this a little bit because there's a lot of like terms to combine, and we'll make the calculus much easier. So HW over 2 squared is HW squared over 4. And then when I multiply this stuff all together, I get pi over 12 times HW cubed. Is that okay with everybody? I have HW squared and HW cubed. Okay, now I'm ready to do the derivative. And this is lovely because this is now just like a power property derivative, right? Power rule derivative. Oops, I forgot my W's on the V this whole time. Not that it really matters. But let's be consistent, right, Mr. Kulik? So I'll do my derivative. And remember, what we're solving for is this derivative when HW is equal to 3. Just reduce that real quick since that's staring at me in the face, might as well. All right, let's start plugging in then. dV dt was 2. HW is 3. So if I multiply both sides by the reciprocal by 4 over 9 pi, I get 8 over 9 pi. If I type that into my calculator, let's do it the smart way this time. I have to muck around with a bunch of parentheses. I get 0.28-ish.
That's the same as saying 2 divided by 5 over 4.
It is. And I think my units were meters per minute. Is everybody okay there? All right. This similar triangles trick, if you get a cone, is a good one to remember. Okay, so if you have something with a cone in it, probably the trick you'll need. All right, let's read another problem. It says car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed toward or for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 mile and car B is 0.4 mile from the intersection? All right, let's draw a picture then. Let's say that this is the intersection. So I'll make this car A that's heading west. This will be car B that's heading north. I'm going to assume, well, I can assume that since the cars are heading west and north respectively,
I forgot I left it in the...
you are the one. Thank you, sir. That they're going to be meeting at a right angle, since I know the cardinal directions intersect at a right angle. Everybody's cool with that? Okay. So what shape am I going to be making here? A right triangle, yeah. So let's label our sides here. I'm going to call this side X because it's horizontal, this side Y because it's vertical, and this side Z. Everybody's cool with that? All right, it says car A is traveling west at 50 miles per hour. What is 50 miles per hour going to be? What should I name that? Very good. dx dt. Okay. Car B is heading north at 60 miles per hour. What should I call that? Okay. At what rate are the cars approaching each other? What should I call that? That's dz dt, right? Z is the distance between the two cars. So the rate they're coming together is going to be the rate as Z is changing. What should I be expecting that rate to be? What kind of a number should I be getting there?
One that is greater than.
Well, think about what's the length of Z doing as they're getting closer? So what kind of a number should I be having there? A negative number. Everybody's okay with that? Okay, just from a common sense standpoint. Okay. And it says we're looking for that value when car A is 0.3 mile. What's 0.3 mile going to be?
X equals 3.
Yeah, that's the value for X. And Y is then 0.4 from the intersection. Everybody's okay with this? Okay. What equation would I be using to describe this situation? Pythagorean theorem. Okay. So we know something about dx dt, dy dt, and dz dt, so I'm ready to differentiate right now because I don't want to eliminate any of these variables because I have either need to know about them or I have the quantity that I need about it. So let's go. Oops. Okay. So I can fill in then. Uh-oh. What am I missing? Yeah, so I'm missing my value for z, but that's not a problem because I know x and y, and I know that x squared plus y squared is equal to z squared. So at the instant where x is 0.3 and y is 0.4, I can find that z. Can anybody see the value for z without having to actually solve this thing out? Yeah, well done. That 3, 4, 5 triangle. Now notice that 2 times 0.5 is just 1, right? So yeah, so I just end up with like dz dt over there. So this is what I'll type in my calculator. What do you notice is going to be a problem? It is definitely not negative. So did we make a mistake somewhere? There. So, well, here's what I'll say. John, you're right on one and wrong on the other. We are just going to make this negative, but we did make a mistake as to why we're not getting a negative number. The answer is negative 78, but we did make a little bit of a mistake prior as to why we're not getting a negative. And it goes all the way back to here. Yeah, why should these be negatives? Because the distance to 0, which is what the intersection is decreasing, right? The distance from A to that intersection is decreasing, so their derivative should be negative. Everybody see that? So those should be negatives because the distance is going to be decreasing as that car is approaching the intersection. Now, at the end of the day, John's right. You're just like, hey, I know this answer needs to be negative. I'm just going to make the answer negative at the end. You're probably going to be fine. But again, thinking about what's actually happening here, like, oh, this is a rate that's actually decreasing the distance, needs to be negative, which is tough to read right away. Until you've done a bunch of these, you don't look for that. You know what I mean? This is the first time we've had to take one of these numbers and make it negative without it expressly saying, like, decreasing. You know what I mean? So, but that's why I picked this example, is it's a good, like, reading comprehension place where that's the trick. It's not the math that's tricky. It's the reading comprehension, like understanding what's going on and like how is this relating to the mathematics involved. All right. We're doing good on time, right? We still have lots of time. Yeah, you guys ask way less questions than first hour does. Or fifth hour, I should say. So, what? Yeah, every consistently, they are double the amount of questions as you guys are. So it's always like.
So do we finish our lectures for this?
Yeah. So it's always just like a question of like not getting too far ahead here versus them. We'll do this last example here, and we'll talk about what to expect here for the rest of or for next week or whatever. Okay. All right. Here it says a man walks along a straight path at a speed of 4 meters per second. A searchlight located on the ground 20 feet from the path is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So let's draw a picture here. There's my searchlight. Okay, the point on the path that's closest to the searchlight is going to be this one. I'm going to call that point O. And then we're interested in here, where the man is 15 feet from that spot. And in your picture, it probably doesn't matter whether you drew that M below O or above O. Everybody's okay with that? And we're told that this distance is 20. And then we have a beam that's focused on the man. Everybody's cool with this? Okay. So let's label this side X and this side Y. Again, the vertical one I'm going to call Y and the horizontal one I'll call X. So this man walking along the path at 4 feet per second is dy dt. Everybody okay with why that is? Okay. So we note here, what can I say about that quantity? Constant. Okay. And then it's asking at what rate is the searchlight rotating? What am I asking for there?
3s.
Yeah, that's asking for d theta dt. When y is equal to 15. Everybody okay with what we've unpacked here? So when you hear rotating, you're talking about an angle. What equation would I write to describe this situation? Yeah, tangent theta equals y over x. Now, what do we know about x? So we'll just call that really y over 15. I'm sorry, 20. Thank you. Okay. You guys ready to differentiate? Okay, what's the derivative of tangent theta? Secant squared theta d theta dt equals derivative of y is 1, and then I get a dy dt. And so now we have some choices here. I'm going to elect to find secant squared theta without using a calculator. Okay. If I use the Pythagorean theorem, side SM should be 25. Hopefully you can notice that that's a 3-4-5 ratio. Right, it's a scale factor of 3-4-5. So I know that secant theta is going to be a hypotenuse over adjacent. So that's going to be 20 over 25 squared. I'm sorry, yes, I wrote it wrong. Thank you. I appreciate when you catch me right away making my mistakes so it doesn't become like I have to change 30 things like 15 minutes later. Not that we'd still be doing this problem in 15 minutes, but... and dy dt was 4. So I will multiply both sides by the reciprocal. That's really, I'm going to reduce that fraction as I go. Oops. Oh yeah. Okay. 4 times 1 over 20 is 1/5. And then 25 over 20 is really just 5/4. So when I multiplied the reciprocal over, I get this, which is 0.128. And the rate here is going to be radians per second. Yes, sir.
You said we have options in the step with the yellow highlight.
Mhm.
What was the other option?
Well, you could have, at this step, you could like use your calculator to solve for theta,
Oh.
and then plug it back into your calculator. Yeah, you could do that also. I just assume use the triangle and just use my trig ratios, my SOHCAHTOA to do it. But like, you could have solved for theta there, you know, with the side lengths of 15 and 20, and then use that to, you know, in your calculator. It would have gotten you the same result, but I think it's more work than it's worth. Or you could have used like one of your Pythagorean identities, right? Like I think that, what is it? It's secant squared plus 1 is equal to tangent squared. You could have used that also, since you had tangent, and you know, like you could have used that also, and that would have been okay. But like, now you're just splitting, you know. What I think, the way I did it, I think was the easiest way to do it. But you could have done lots of things at that step. All right. What do you guys think? Yeah, the hardest part is like getting some practice in to where you can build some intuition up, to where you can look at these quantities and go, okay, I know what that is. Okay, I know what that is. Okay, well, I know what that is. It's like, okay, here's my equation. Do I have everything I need when I differentiate? No, I don't. Okay, how can I reduce a variable? And like picking up some of these tricks, right? Because most of this is about reading comprehension and making sure you really understand what everything is. You've labeled things accordingly. You know what I mean? All right. So next time we meet, we'll do some more we'll do some more examples or some practice together. I'd like to try the last part of class to do a homework quiz on this topic. The format that I'd like to do on that is I'd like it to be a partner exercise. I have, I think, I don't know, like 5 or 6 of these problems that I've kind of squirreled away that everybody will get like a different pair of problems. And basically, like, the way I would score this out is if you can, you know, like do some of the setup, at least it's an 8. If you can get one right, it's a 9. If you can get both right, it's a 10 kind of thing. It's kind of what I would imagine wanting to do with something like this. Now, when we come back and there's like, okay, like this, when the homework went terribly, like I can't get any of these, we can always punt and make, you know, do that later or whatever, and just spend a day like working through some stuff. So don't feel like this is written in stone. But does that seem like a reasonable setup? Yeah,
So I'm
Teagues?
saying it's only 3.9.
Only 3.9. Yeah, only 3.9, thanks.
And like up to what we've learned today, correct?
I would say like, yeah, it wouldn't be like absurd. The 5 or 6 problems that I have are of like differing levels of difficulty. So like depending on which random pair you got, you might get, you know, like 2 that are harder than, you know,
Yeah.
like not everybody's going to get the same problems, because that's the point of like having you guys have partners. You're going to be talking about stuff. I don't want everybody with the same 2 problems, or it's like,
Then it's a class wide.
then it's, yes, exactly. So everybody's going to get like a pair of problems, and some groups might have like 1 problem in common, but nobody's going to have 2 problems in common, you know, and like the group next to you probably has 2 different problems than you anyways.
Yeah.
You know, like I can make up a lot of, you know, there's 30 different combinations of ways to dole out 6 questions into 2 groups of 2. So I think I'll be okay there. But that's kind of what I'm thinking. And we can talk some more on Tuesday when you guys come back, if you're just like, this was an unmitigated disaster, like we can't do this right now. It'd be okay. That's fine. This is typically a difficult topic. So don't be frustrated. My suggestion to you, if again you're doing one of these problems and you're stuck, start all over, reread the problem, redraw the picture, think about like, okay, am I doing everything exactly the same as I did last time when it didn't work? There must be something I'm missing. Like, make sure that like you've labeled everything correctly. That's like, check the units, make sure the units make sense. If something's like area dt and the unit's cubes, like, well, that can't possibly be right. Or the area or the unit is linear. It's like, oh, that can't possibly be right. But the majority of the mistakes come in the setup piece. Like the calculus is easy when we get to the calculus part, right? The algebra after you've done the calculus is easy. It's just getting to that point where you're ready to differentiate is usually the hard part. That's typically where if you're going to make a mistake, that's the place you'll make your mistake. So it comes down at the end of the day a lot of just like reading comprehension. Can you really understand what it is that you're reading and like turn it into mathematics, which is like kind of a soft skill. It's not like the same every time. You have to kind of sit and think about it. Which is like, how do I practice this? How do I get good at it? And it's like, it comes down to reps. It just comes down to reps. Like slowing down and like seeing examples of like, oh yeah, something different happened here. What else could have happened? And just like, okay, got to remember that can be something that comes up. And just kind of building out a toolbox on this. And then we have one more section in chapter 3, and then we're done.
So our next test is going to be on
3.6 through 3.10.
Okay, yeah.
So you'll see some log differentiation again. And I will recycle like some derivative questions from the first. I will have like a couple of like 2 or 3, like just show this derivative is equal to this, just to kind of keep in touch with those skills from 3, like chain quotient product, those basic derivative rules that we have to be able to use all the time. We have to be good at them. Can't go away. So there'll be like, I don't know, I'd say like 25% of the points will come from like a couple of questions like that, or at most like 25% of your points would come from some more questions like that. They'll all be shows. My hope is that they all kind of have like a trick that can make them either horrible or pretty easy. That if you do the algebra in the beginning, you can take something that would turn into horrible into something pretty easy.
Yeah.
If you're like sensible about things. Or at least, some of them being like, this looks like it's going to be horrible. Wait a minute, am I doing something dumb? Like not combining some like term or something, or avoiding a product or quotient property when I don't have to do it. You know what I mean? So the test certainly won't be next week, but it'll probably be the week after. Unless that runs into we have asynchronous days at some point.
Yeah, it's not next week, it's going to be the week.
Yeah, so
it's going to be Thursday and Friday.
Yeah, we'll see how that comes. I would like to do the test before the asynchronous day, and then just have like your asynchronous assignment would be like, here's like 10 AP multiple choice questions to practice on. Have fun. Like it's, like 30 minutes of something, but like take a brain break rather than have the test wrap through that and have you guys stress yourselves out to no end, going crazy on it. But if it is what it is, if it has to land there, then it'll land there. You know, be no big deal. We'll figure it out.
For this 3.9 section, can we complete all the way up to question 27?
Yeah, we've done all the examples I was planning on showing you guys.
Okay.
So I think you should be capable of doing them. Now, again, do I think that you're going to come back on Tuesday and be like, yep, that went swimmingly? Nope. So if you're getting stuck, that's okay. Just skip the question, go to the next one, because these are problems where what turns out to be the hard one is maybe not always obvious, or they don't actually like go in. I mean, they're supposed to be going in like ascending order of complexity, but the thing that trips you up in one may not be in the next one. So it's just, you know what I mean? Like you might see the trick on 27 and you didn't see it on 19 or something. You know what I mean? Like don't quit because you got stuck on one. And just be like, I don't know anymore. Just keep going. Just skip it and go to the next one and see what you can do. You know what I mean?
Yeah.
Overall, so this weekend, right? Sunday's problem set?
Yeah.
3-6, 3-7, 3-8. 3-9's not due Sunday. Next week we'll worry about 3-9. Okay. So you're looking at 3-6, 3-7, and 3-8. Remember 3-8's wimpy, it's like 6 problems. I think we've done half of them now.
Yeah.
After today's in question, so it shouldn't be much of a roadblock there, and they're relatively easy. Well, almost no calculus in these problems. Like all the calculus is like conceptual stuff.
Yeah.
The actual functional symbol pushing is all algebraic, it seems like. So those should be relatively easy ones. Everybody feeling okay in general? Not bad. Does this feel like it's getting easier as we're going?
That's it's math.
Like it's getting less conceptual, right?
Yeah.
It's getting more symbolic. That can be good or bad depending on who you are. But I think the goal will be to try to finish chapter 4 before the final. So we should have the rest of November through the middle of December. We have a month or so to do chapter 4, I think is probably realistic.
Chapter 4.
I don't think so. Chapter 4 is a little bit of a grab bag of a chapter also.
Okay.
So it's not like, this chapter I think is rather focused, where it's just like derivative rules for the first half, application on the second half. Chapter 4 is a bunch of weird topics all kind of jumbled together in it, where there's like a 3-section run where all this stuff makes sense to have together, and then there's like, oh, and then we'll have this random section here and this random section here, and like they couldn't figure out when to do some of this stuff.
Yes, they just kind of put it all together.
You know, like one of the topics in chapter 4 is like L'Hopital's rule, which is a way to, you remember when you're doing limits and you get the indeterminate case?
Yeah.
There's another technique that you can use to get around an indeterminate case, but you need to have derivative calculus to be able to use it. But basically,
so that's why I couldn't go in chapter,
that's why I couldn't go in chapter 2,
but,
but it's like kind of a standalone idea. Essentially what L'Hopital's rule says is the limit of f of x is equal to the limit of f prime of x. So if you end up with an indeterminate case, just keep taking the derivative until you can evaluate the limit.
you can do that.
That's what L'Hopital's rule says.
Dang. This guy.
But like, again, that's a conceptually really pretty easy idea. The problems can get like, you know, like you've seen that limit problems can be hard. You've seen that derivative problems can be hard. You're now mashing two of these things together.
Yes.
You know. And then you have a bunch of like, we talked about earlier in this chapter when we talked about like those velocity problems and like increasing and concave up or whatever was like a thing, and there's some derivative tests for like finding maxes and mins that we'll deal with in that chapter that are based around those ideas about how you can check like how you can find maxes and mins for any kind of a function without having to graph anything, like a non-graphical method to finding maxes and mins. Where you basically take the derivative, set it equal to 0, and then check whether that point is like concave up next to concave down next to concave up, whether it's going to be a minimum or a maximum, or like some neither point where it's like flattens out and then continues going up or down or whatever. But there's like, that stuff is in there. The mean value theorem pops up. I haven't seen the mean value theorem in a while. We saw the intermediate value theorem before. The mean value theorem is different, but it's kind of the same idea. It's basically saying that if you have a continuous function, that somewhere between your starting point and your ending point, somewhere in it passes through the average value of those two y coordinates, which of course it does. It's just like the intermediate value theorem again, but like that's something that's like a whole chapter of mean value theorem stuff. Or I'm sorry, a section of mean value theorem stuff. Yeah, not a chapter.
Pretty popular.
It is a very popular AP exam question topic.
Really?
Yeah, the mean value theorem comes up a lot, as does intermediate value theorem. These are things that like anything that gets a name with theorem in it is something that you're going to see AP test questions with it. But it's like it's kind of a weird chapter where it's like there's no new derivative stuff coming in. Like we're not learning more techniques to do that kind of stuff. It's just like more kind of like theoretical application things. Like how, not like practical application so much, but it's like, how do I find the max or min of something? How do I, prove that this somewhere along this we get this value? How do I, yada, yada, yada. Like, oh, here's another technique for doing limits. It's a little less tedious than some of the shortcuts we had to take before. Like if you remember on one of those, like on the first test or whatever, that last question where there was a limit on there that you had to do, and like to get through the limit, you had to like you had to do a difference of 2 square factoring and a difference of 2 cubes factoring, and like it was like a colossal pain in the butt. It is a simple L'Hopital problem. If you just do the derivative of the top and bottom, which are both like easy things to differentiate with respect to the variable in question, it just like bloop, falls right out. It's like a one-stepper instead of like this, like a page of factoring and like like grinding. It's like, oh, this would have been nice. And then I think we start the foundations of integral calculus at the end. Optimization is in there. That's a big topic. Yeah, that's like that'll be But I think it's only 7 sections or 8 sections. Optimization is in there, so that's a good one. That's another tends to be kind of tricky topic, similar to these related rate problems, because it's again about story problems and reading comprehension. But there's only 8 sections in chapter 4. We're doing all of them, but I think some of them are like symbolically really easy. Like there's not, like the calculus parts aren't hard, the algebra parts aren't hard, they aren't complicated, they're not long, but like you have to understand what you're doing.
Yeah. Like
conceptually maybe it's a little bit difficult, but it's not even that bad compared to like the heavy theory we saw at the beginning, because we've established most of the heavy ideas. We're still just talking about application, which is usually easier than like the basic theory. But that was the goal, is to finish the first 4 chapters in semester 1. I think we'll be able to do that. We'll decide if there's going to be 1 test or 2 tests in chapter 4. I'd like to do 2 in there. It feels like 8 is a lot for 1. 8 sections would be a lot of tests for 1.
How many sections was in chapter 2?
But too many. I should have made more than 1 test. That's why it ran so long.
Yeah, that was a long.
Right.
Long test.
So like I screwed that up. But hopefully everybody still felt that the options I gave you on that was fair and reasonable for what happened. Yes, or Paul.
Do you know what our finals are like? Just kind of feel like finals we've had in the past where it's like just some questions in each section. Or
I haven't written it yet. I haven't taught the course here before, so I don't have anything that I've done previously. So I have to really sit down and think about what this would look like. What my starting point would be, my initial instinct would be like, okay, I'm going to have a block of questions that are chapter 1, 2, 3, 4 questions, and say, okay, you have to complete like 20 points. You have to get like 20 points out of each of these 4 sections, and there's like 30 points worth of questions. You know, like,
Oh, yeah.
like you can earn up to a max score of 20 in the section, but you can get that 20 points however much you have enough time to complete. You know what I mean? That would be kind of my initial, like where I'm kind of initially at, is to weight each chapter evenly. Like we're going to put the same, you know, and have like more than you need to get a perfect score in each of these, and just, but I have to like, that's my initial thought. Now, if I have to write this thing out and look at, is this even something that's realistic to complete minimally in the time that we have?
How long do you have for example?
I don't remember, to be honest with you.
we don't have a second semester.
Correct. Yeah. Any student,
We do, but like.
any
not-
student taking the AP exam would not be required to take a final for the course. And I would say that Mr. Kulik would not even offer the option. Like, I don't want to write a final. You should not be taking a final. I will be very honest with you. Like, just worry about the AP exam. That'll be enough. I think with the way that, again, when I went through and looked at things, the hope would be to have a week or 2 at the end where we've cleared the content we need to clear, and we're going to be like, here's a set of free response questions from a previous AP exam. Like, that's your homework. We're going to come back tomorrow and go through them. You know, like, here's a multiple choice, like AP section, previous AP test. Like, take this home, put a clock on it, see what you can get through. We'll go through it in class the next day. You know, like, to have a couple of 3 or 4 classes where we're just doing that is kind of the hope at the end. Oh, I talked a lot.